Lorentz had left physics in a mess. Bring in Einstein. Einstein came at this problem from a completely different standpoint. While Lorentz had derived his equations on the assumption that they should leave the Maxwell equations invariant, he still accepted the ether and rejected the principle of relativity, because he did not believe it was possible to make the principle of relativity consistent with both electromagnetism and mechanics. Einstein disagreed. He believed that the experimental evidence of the constant speed of light and the invariance of electromagnetism was further evidence for the principle of relativity, and that the principle could be obeyed by both electromagnetism and the laws of mechanics. He adopted two postulates: the experimentally observed property of the speed of light, that it was constant in all reference frames, his hypothesis that the principle of relativity was correct. All laws of physics should be the same in any reference frame moving at constant speed, and it should be impossible to say that one frame is moving and another is stationary, because motion is relative. From these postulates, Einstein was able to rederive the Lorentz transformations far more simply than Lorentz had done, compelling evidence that Einstein's postulates were on the right track. Once he had done this, his next problem was to make the laws of mechanics consistent with relativity. He discovered that he could do this with a simple correction to Newton's idea, and that was that the mass of an object should increase with its speed. The faster you go, the heavier you get. With this basic idea, everything falls into place. Although it is hard to understand exactly why mass must increase without following through the mathematics, it is possible to understand how it explains one particular aspect of relativity with the laws of mechanics. One of the consequences of the Lorentz transformations is that it is impossible for any object to travel faster than the speed of light. So what happens if you accelerate an object to just under the speed of light and then give it a kick? According to mechanics, the force of the kick will cause the object to accelerate, and it will overtake the speed of light. Any attempt to reconcile relativity and mechanics must explain why this does not happen. Einstein's proposal that the mass of an object increases with its speed says that as the speed of an object approaches the speed of light, its mass approaches infinity. You could kick an object just under the speed of light if you wanted to, but it would be so massive that the acceleration produced could not cause it to reach the speed of light. The speed of light is unattainable for any object with mass. When Einstein calculated by exactly how much the mass of a moving object should increase, he discovered the remarkable fact that the increase in mass was directly proportional to the object's gain in kinetic energy. The constant of proportionality was the speed of light squared. This led Einstein to propose his most famous equation, E equals mc squared. The consequences of this equation are startling. Before Einstein, we had two quantities which we thought were completely independent of each other. Energy was an abstract mathematical quantity which came in two forms, kinetic and potential, and given any arrangement of particles we could work out the size of each form, with the knowledge that if we came back at a later time, the sum of the two forms would add to the same value. That is conservation of energy. We didn't know what energy was. That question seemed meaningless. Energy was just a mathematical tool which was useful in solving problems because it was conserved. Mass, on the other hand, was a completely different property of matter which described its tendency to resist changes in its velocity. If you try to push a heavy object, it will be harder than pushing a lighter object. What Einstein showed was that these two seemingly unrelated quantities were in fact exactly the same thing. When we were calculating energy, we were also calculating mass, and vice versa. Energy and mass are simply two different unit systems for describing the same quantity, and the speed of light squared provides the necessary conversion factor between those two systems. Why was this equivalence between mass and energy not noticed before? It is because energy, or mass, or whatever you want to call it, comes in three distinct forms: rest energy, kinetic energy, and potential energy, and at non-relativistic speeds almost all of the resistance to motion comes from the rest energy, because that is far greater than the kinetic or potential energy. So we originally referred to the rest energy as mass, and believed it to be distinct from kinetic and potential energy. What is the use of Einstein's equation? Does it need a use? Relativity itself has become a fundamental pillar of modern physics, and its practical applications are diverse. But E equals mc squared has a particularly infamous application in warfare. When scientists measured the mass of a uranium atom, then measured the mass of the two products it decayed into, they found a discrepancy. Before Einstein this would have been bizarre. It would violate conservation of mass. But after Einstein we know that mass and energy are different words describing the same thing, and the discrepancy in mass is really a discrepancy in rest mass. or rest energy, so the remainder can be accounted for through kinetic energy. Using Einstein's equation, scientists could calculate exactly how much energy would be released when a uranium atom decayed, and when they discovered just how large this energy was, its applications in both warfare and power became apparent. How can we get a better understanding of relativity? It is hard to get an intuitive feel for relativity because all of its principles are derived from trying to make existing theory fit with new experiment, and this leaves the physics in a mess which is hard to sort out. Is it not possible to get a better feeling for why relativity is true? The answer is yes, and it was provided by Hermann Minkowski, a mathematician who proposed an alternative formulation of Einstein's relativity, based on non-Euclidean geometry, an abstract branch of pure mathematics. Minkowski realized that the Lorentz transformations could be derived by assuming that time is simply another dimension, like the three dimensions of space. The concept of changing your velocity in three-dimensional space is then replaced by the idea rotating in four-dimensional space-time. We then get a better understanding of phenomena such as length contraction and time dilation. If you take a three-dimensional object and project it onto a two-dimensional screen, like a computer screen, and then rotate it, you may see its width shorten, for example, while its length widens, because you are looking at it from a different angle, a different perspective. The same is true of space-time. If you rotate your axis in space-time, that is, look at something while moving at a different velocity, you will see the length change, length contraction, but also the time separation between events change, time dilation. It is important to stress that time is not exactly the same as space. It behaves slightly differently, the key difference being a change of sign in one of the calculations. For any mathematicians out there, it is interesting to note that the Lorentz transformations can be derived in their exact form if you take four-dimensional space-time to be a simple extension of three-dimensional space, but choose your units for measuring time so that the speed of light is equal to the imaginary unit, the square root of -1. You then simply use the normal equations for transformation of coordinate systems upon rotation. When you convert your units back into meters and seconds, the imaginary numbers will disappear and you will be left with the Lorentz transformations. I hope that you have a better understanding now of what relativity is all about, although a true understanding cannot be achieved without studying the mathematics behind it. If you have any further questions, please post them in the comments and I will try to answer. Although I can't promise anything, as I said at the beginning, I am learning this stuff too. This video is as much for me to go through the process of collecting my knowledge and putting it into a logical order, as it is for you, the viewer. Thank you for watching and goodbye.